Hello everyone and welcome back to our physics revision class. So today we'll see Unit 8, which is about properties of bulk matter. So as you know, in this chapter we have three main important parts or points. The first one is about elasticity, and the second one is about fluid mechanics, and the third one is about heat and temperature, okay? So we start by defining what elasticity is. Elasticity is simply defined as the property of objects by virtue of which they can regain or restore their original configuration after the removal of an applied force or a deforming force. So the force which is responsible for the changing of configuration of objects is called a deforming force, okay? But this property of elasticity continues only to a certain limit. To that limit, the limit to which materials keep their elasticity is called elastic limit, okay? So when we exert a deforming force, we have a quantity or a variable which we call a stress. A stress is simply defined as the force exerted on an object per unit area. So we can put it as stress is equal to force over area, okay? Force over area. And we have, whenever a deforming force is exerted on an object, we have a strain. A strain is simply a fractional change due to the deforming force. So a strain on an object can be defined as the change in configuration. It can be a change in length or volume divided by the original configuration. Okay, for example, for tensile strain, we have, it can be like change in L divided by original length, or it can be changing A over original area, okay? So this elastic materials is governed by what we call the Hooke's law. Hooke's law simply states that so the stress we exert on objects is directly proportional to the strain. So stress divided by strain is called modulus elasticity of the particle or the material. So we have different kind of modulus elasticity. The most common one is called Young's modulus. So Young's modulus is simply tensile stress over strain, that is force over area divided by change in L over original length, okay? And we can also have a bulk modulus and shear modulus, all right? So whenever a force is exerted on elastic materials to deform them, they start to store energy. The energy stored on this elastic material is called strain energy, and mathematically strain energy is equal to the work done on the object by the force. Okay, so since the force in the displacement, fractional or the changing configuration are directly proportional, so we take the average force, that's F over 2, so the total energy or the strain energy stored in a deformed object or in an object under a deforming force is given by E is equal to half times F times X, okay? So this is all about the elasticity of materials. So next we will see about fluid mechanics. So in fluid mechanics we have two important parts. The first one is called fluids at rest, that's fluid statics, and the second one is fluid dynamics. So in fluid statics, we have defined what we mean by a pressure. A pressure is simply defined as the force exerted on an object per unit area. So a fluid in a liquid, for example, at this part of the liquid, all the mass of the liquid above the surface exerts a force. So that force is given by mass of the liquid divided by, multiplied by the gravitational acceleration. So divided by area, okay? So this is how we define pressure, okay? But so this is a measure of area, but we know that mass can be also expressed as mass density times volume times G over area. But the volume is, if this is H and if this is A, then we can replace the volume with rho times A times H times G divided by A. Finally, we come up with an expression for the pressure inside a liquid by P is equal to rho GH, okay? The density times the gravitational acceleration multiplied by the depth with H, okay? So you can simply tell that the pressure inside a liquid depends on the depth of the liquid, okay? The greater the depth, the greater the pressure, okay? And we can also calculate the total pressure. Total pressure inside a liquid is given by the atmospheric pressure multiplied plus the gauge pressure, that's rho gh. The atmospheric pressure is the pressure that the atmospheric air is exerting on surface, okay? For example, at sea level, the atmospheric pressure at sea level is equal to 1.01 times 10 to the power of 5 Pascal, okay? This is how much the atmospheric air is exerting, how much pressure the atmospheric air is exerting on sea levels. So another important term, the concept on fluid statics is about Pascal's principle. Pascal's principle is a principle that says that whenever an enclosed fluid, whenever a pressure is exerted at one point, then the pressure will be distributed evenly without diminishing everywhere. So pressure at this point is equal to, when we exert a pressure, for example, at this point, this pressure will be distributed evenly throughout the volume of the liquid, okay? So with the help of Pascal's principle, there is a hydraulic lift force multiplying machine. So simply, as you can see, this is an enclosed fluid. Inside the fluid there is a piston, a smaller piston of area A1 and a larger piston of area A2. So when we exert a small force here, there will be a pressure in this part of the liquid, but this pressure, according to Pascal's principle, will be distributed throughout the fluid, okay? So there will be the same kind of pressure here. So there will be a pressure here. So by definition, we know that P is equal to P. So the pressure at this point is equal to the pressure at this point. The pressure at this point is force 1 times area 1 is equal to force 2 over area 2. So solving for force 2, the force 2 will be force 1 times area 2 divided by area 1. Since area 2 is greater than area 1, then F2 will be greater than F1. So by simply exerting a small force here, we can uplift a larger load on the other side of the hydraulic lift. So this is how a hydraulic lift is working. So there are also some important concepts on fluid statics, like the surface tension. That's the property of fluids to act like a stretched plastic due to cohesive force. There's also a capillary action, which is due to adhesive force, the force between the molecules of the liquid and the molecules of the containing material, okay, of the liquid. So you can read that on your texts. So the other important part of fluid mechanics is about fluid dynamics. So that's the kind of physics that studies how the motion of fluids, okay? So in fluid dynamics, there are two important principles or equations. The first one is called the equations of continuity. In equations of continuity, it's based on the law of conservation of mass that passes through a given cross-sectional area inside a pipe. So as you can see, we have two parts of a pipe. This is a wider one and this is a narrow one. So we are assuming that the speed of the fluid at this one is V1 and at this part of the pipe is V2, okay? So from the law of conservation of the rate of mass that passes through this point 1 is equal to the rate of mass at same M2 over change, okay? So we know that mass is V times density, V1 times density, that's the volume, over change in T is equal to V2 times density over change in T. We know that the fluid is the same, so they have the same, it has the same density. So we know that the volume for this, for example, for this portion of the volume is equal to area 1 times length 1 divided by change in T, which is equal to area 2 times length 2 divided by change in T. But length is the length of the length that the fluid travels per unit time gives us the speed at which the fluid is moving, so that finally we come up with the expression for the equation of a continuity as A1 V1 is equal to A2 V2, okay? A1 V1 is equal to A to V2. So this is what we call equations of continuity. So from this mathematical expression, you can tell that whenever the area of the pipe is increasing, the velocity at which the fluid is moving through it decreases, and when the area of the pipe decreases, then the speed increases, okay? The speed increases. So the second important principle in fluid dynamics is Bernoulli's principle. So the Bernoulli's principle is basically based on the law of conservation of energy. So the total amount of the mechanical energy of the fluid inside the pipe is always constant, okay? So let's consider 2 points in this pipe. As you can see, this is point 1. At point 1, the velocity of the fluid is V1, and at point 2, the velocity of the fluid is V2. And point 1 is found at a height of H1, Y1 from the surface of, and position 2 is found at height of Y2. So the pressure at point 1 is P1, and the pressure at point 2 is P2. So generally, from the law of conservation of energy, the total energy in this pipe at any point is constant. That is the pressure plus half times, that is due to the kinetic energy of the fluid, half times V square plus rho G, this is gravitational potential energy, is always constant, okay, constant. So from that, we can tell that P1 plus this is the work done due to the pressure, kinetic energy, this is potential energy, is total energy is always constant. So this is basically what Bernoulli's principle states, okay? So the other concept on Unit 8 is about heat and temperature. So normally we know that temperature is defined as it's a quantity that tells us the amount of hotness or coldness of an object. Or in another way, we can also define temperature as the measure of the average kinetic energy possessed by the particles of a system. So heat and temperature are not the same things, but they are very related to each other. So heat is a form of energy that transfers from one point to another point, or from one object to another object due to a difference in temperature, okay? Without a difference in temperature, we cannot talk about heat, okay? So heat is a form of energy that is in progress or in transfer between two objects or between 2 points due to the difference in temperature, all right? So the amount of heat energy that is required to heat an object depends on two quantities. The first one is the mass. So the greater the mass, the greater the heat energy required. And the second is the temperature difference that's required, okay? So we know that Q is directly proportional to m times change in T. So Q divided by m times change in T must give us some constant, and that constant is called specific heat capacity. So specific heat capacity of objects is defined as the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius or by 1 degree Kelvin, okay? So this is basically the main concept of chapter 8. I hope you find this very useful. So after this, I will send you some worked examples on each unit. So that's it.